New chapter, some basic concepts of organic chemistry. See, already we studied about the carbon compound. The carbon having some unique properties. They are called catenation because they forms covalent bond with carbon and also forms covalent bond with other atoms like hydrogen, oxygen, sulfur, nitrogen, etc. So here then halogen, phosphorus also. Halogens, phosphorus, so like this. So this resulting compounds are studied under a separate branch of chemistry is called organic chemistry. Now the first how it is obtained, which first of all Wöhler, F. Wöhler, the scientist synthesized an organic compound, that is urea, from an inorganic compound, that is ammonium cyanide. Ammonium cyanide is a inorganic compound, NH4CNO, that is ammonium cyanide. The ammonium cyanide on heating it converts to urea, which contains in our human body. So that is called organic compound. So this is called urea. The same here. Look at this, N2H4CO. Here N2H4CO, like that. So the same, the molecular, only the structural arrangement is differ. So the ammonium cyanide on heating it appear urea, that is called organic compound. Okay. Then the tetravalency of carbon. The tetravalency of carbon is shape of the organic compound. The shape of the organic compound is the fundamental concept of the molecular structure, helps in understanding and predicting the properties of organic compound. Already you learned that valence bond theory, molecular orbital theory, that molecular structure like that you are studying in chemical bonding. And also you already know that the tetravalency of carbon and the formation of the covalent bond by it are explained in terms of the its electronic configuration and the hybridization of s and p orbitals, like this. So here it may be recalled that the formation of the shape of molecules like methane, CH4, ethane, CH3, simply they are called C2H5. We can write this like C2H6. So then ethene, C2H4, ethine, C2H2. So they are explained in terms of the sp3 hybridization, sp2 hybridization and sp hybridization. So that is the hybridization influences the bond length and the bond enthalpy in organic compounds. Here the sp hybridized, this is sp and this is sp2 and these are sp3 hybridized orbital. Here the sp hybrid orbitals contain more s character and hence it's closer towards the nucleus and forms shorter and the stronger bonds than the sp3 hybridized orbitals. Then the sp2 hybridized, the sp2 hybridized orbitals is intermediate in s character between sp and the sp3. Hence the length and the enthalpy of the bonds it forms also intermediate between them. Okay. So the change in the hybridization affect the electronegativity of carbon. The greater the s character, greater the electronegativity. The greater the s character of the hybrid orbital, the greater is the electronegativity. So the carbon atom having an sp hybridized orbitals with 50 percentage of S character that is more electronegative than the possessing sp2 or sp3 hybridized orbital. Okay. Then the some characteristics features of pi bond. See, the pi bond formation, that is a parallel orientation of the two p orbitals of adjacent atom is necessary for a proper sideways overlap or the lateral overlap. So for example here H2, see there is CH2 double bond CH2, this is ethene. The ethene molecule of all atom must be in the same plane. So the p orbitals are mutually parallel and both the p orbitals are perpendicular to the plane of the molecule. So rotation of one CH2, this is the one CH2 fragment with respect to other interferes with maximum overlap p orbitals, and therefore the such rotation about the carbon-carbon double bond rotation. That is, so here the carbon-carbon double bond rotation is restricted. Then the electron charge clouds of pi bond is located above and the below plane of the bonding atoms. So the result in the electron being easily available to the attacking reagents. So in general, the pi bonds provide the most reactive centers in the molecule containing multiple bonds. So that the pi bond pi bond compounds are easily most reactive compounds. Then we'll see the structural representations of the organic compound. Here the structural representations of organic compound complete, condensed and bond line structural formulas are we are going to see. See, the structure of organic compounds are represented in several ways, that is the Lewis structure or dot structure, dash structure, condensed structure and bond line structural formulas are some of the specific types. Okay, so the Lewis structures, however, can be simplified the representings of the two electron bond in dash. See, simply this is called bond. This contains two electron. Simply we can write like this, that is two electron. This one single bond contains two electrons. So such a structural formula focuses on the electrons involved in the bond formation. So a single dash represents a single bond. So double dash is used for the double bond and the triple dash represents for the triple bond. So the lone pair of electrons for heteroatoms like oxygen, nitrogen, sulfur, halogens, like this, they contain lone pair, that means unshared electron pair. So may or may not be shown. We will see. For ethane, ethene and methanols of the structure. Say look at here. This is the compound methane. The molecular formula is CH4. We can write the structural arrangement like this. So this contains two electrons. For example, already we seen that here. I'll write here. So carbon having, that is 4 valence electron. Then the hydrogen having 1 valence electron. This hydrogen having 1 electron and this hydrogen having another 1 electron, and this side this hydrogen having one more electron. Already I said 2 electrons contain one single bond. So we can write it like this. This one single bond, this one single bond, this one single bond and this one single bond. So this is called a structure of methane. Can you understand? See, this is methane, the structural formula for methane. Then next is ethene, the double bond. Carbon having like this, the same similarly, this is the this having 4 electrons, this 2 electrons, this 2 electrons, this 2 electrons, this 2 electrons. Now you can count, so 8 electrons in this carbon atom, and this carbon atom having 8 electrons, hydrogen having duplet, so all are matched. So this is the structural arrangements of ethene. Then look at this carbon-carbon triple bond. This is compound containing that is triple bond, so ethine. So now check at this carbon 8 electrons and this carbon having 8 electrons. This hydrogen 2 and this hydrogen 2. So that this is the structural arrangements of the ethine compound. And the methanol. The compound containing lone pair of electrons. So here the oxygen having lone pair of electrons, that is unshared electron pair. You can write like this, or you can write simply, you can leave it without mentioning the lone pair of electron. That is also correct in the structural arrangements. So this is the structural arrangements of the methanol. So you can write like this, or you can write, you can show the lone pair of electron also. Both ways correct only. Then, so the structural formulas can be further abbreviated by omitting some or all of the dashes, like all of the dashes representing covalent bonds and indicating the number of identical groups attached to an atom by the subscript. Then the resulting expression of the component is called the condensed structural formula. So this condensed structural formula, this for ethane, methane, like this one you can write it. The ethane, simply you can put CH3, CH3. No need to write the dashes. Simply you have to write the subscript, the number of hydrogen atom. Here also that this is ethane. For ethene, this compound having, that is CH2, we can write it like this, CH2, CH2. So here you have to mention the double bond, okay. So CH2 double bond CH2. Then simply you can write like this, CH2 double bond CH2. Then ethyne, simply you can write it CH triple bond CH. Then methanol, you can write it CH3OH. Okay, so this is the condensed structural formula. Then similarly you can write in long chain carbon atoms also, hexane, heptane, octane, nonane, like this. Then for example, suppose if you have octane, means that is this condensed formula, structural formula, you can write it CH3, CH2, 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 1, 2, 3, 4, 5, 6. Suppose if I write hexane, so you can write it that CH2, how many CH2s are present here? 1, 2, 3, 4. So you can write it CH3, CH2 is 4 times. So just write and put in a bracket CH2 4 times, again the terminal CH3. So this is also indicate hexane. Not only that hexane, the long chain carbon atom, the number of CH2 group, you can write it that in subscript, that is count the total number of CH2 group and write in the subscript, bracket subscript. So further simplification of organic chemistry used another way of representing the structure, that is in which only lines are used. So in this called bond line structural representation of the organic compounds. So the carbon and hydrogen atoms are not shown and the lines representing the carbon-carbon bonds are drawn in zigzag fashion. So the only atoms specifically written are oxygen, chlorine, nitrogen, sulfur, etc. So the terminal denote methyl group, okay, unless the indicators otherwise the functional groups. So while the line junctions denote carbon atoms bonded to appropriate number of the hydrogen required to satisfy the valency of the carbon atom. So we can see here the example. Example 3-methyl octane. So this is the representation way. You can write as octane means what? 8 carbon atom. Here the third position containing 1 methyl group. So 1, 2, 3, 4, 5, 6, 7, 8. So the long chain is A octane then one methyl position is contained. 3 position having methyl group. So this is the way you have to write one way, and next way you can write it like this: CH3, the CH2, CH, then the CH3, CH2, 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 then the CH3. Or you can write it, the third method as bond line method, that is the zigzag fashion. So here 1, so here also now count this terminal group. This is a terminal group. This is a terminal group, and this is also one terminal group. The 3 terminal groups is called methyl group. The terminal position is called CH3. We can write it like this. Then count it now. Here one carbon, this one carbon, this one carbon, this one, this one, this one, and this. So totally 8 must be there. 1, 2, 3. I will write here 1, 2, 3, 4, 5, 6, 7, 8. So according to the formula, molecular form methyl octane, the third position containing methyl, third position, so that I am writing like this. So this is also right method. This method is called the structural formula, bond line formula. Okay. Then the various way of representing and with functional group, containing functional group, for example 2-methyl bromobutane, 2-methyl bromobutane. So you can write it 2-methyl, not 2-methyl, 2-bromo. Right here, 2-bromobutane. Suppose if you second position having bromine, so that you can write it CH3, CH, Br like this, then CH2, CH3. Then another way is called this way, that is CH3. Then you have to write like this, that is CH. So this Br having like this, so this Br, then remaining CH2, then CH3. So this is another way. Then the bond line formula, you can write it, the CH3 terminal group, then this having one Br, CH2, then CH3, so Br you have to write like this. So the 3 methods are there. You can write it this method, or using this method, or using this method. So all these are correct only. So this form, this arrangement of which molecule means 2-bromobutane. Then the cyclic compounds, we can write the bond line formulas. For example, cyclopropane. The cyclopropane is simply, you can write it, that is CH2, 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 like this. So this is the cyclopropane. Or we can write in the bond line formula, just put a triangle. This having CH2, this having CH2, and this position is CH2. So this is cyclopropane. Then the cyclopentane, we can write it like this. Here I will write cyclopentane, the CH2, CH2, then CH2, CH2, CH2. So this is cyclopentane, or we can write it simply just like this. This is also one of the method. Then the cyclohexane, also the same way you can write it. I will write here CH2, 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 then CH2, 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 then CH2. So this is the cyclohexane, or you can write it like this. This is cyclohexane. This is a cyclic compound, not an aromatic compound. This is not a benzene, okay? This is a alicyclic compound, okay? So here the next is a 3D representations of the organic molecule. Here the 3D structure of the organic molecules can be represented on the paper by using the certain convention. For example, using the solid line and dashed line, there is a word formula, and the 3D image of the molecule from the two-dimensional picture can be perceived. So in these formula, the solid wedge is used for the indicate the bond projecting out of the plane of a paper. This, okay. Then the towards the observer, okay. This is towards the observer. Then the dashed line used to depict the bond projecting this. Bond projecting out of the plane of the paper and away from the observer. Okay, wedges are shown in such a way that the broad end of the wedge is towards the observer. The bond lying in the plane of the paper are depicted by using the normal line like this. Okay, so the 3D representations of the methane molecule having like this. So this two bonds, this hydrogen and this hydrogen bond is plane of the paper, okay, plane of the bonds in the plane of the paper, and this dashed wedge is bond away from the observer. This is bond away from the observer, and thus the solid wedge bond towards the observer. Okay, so this is the 3D representation. Next class we will discuss the classifications of organic compound.